the last subtopic that we have to do over here is thermodynamic scale of temperature. It's sometimes called standard scale of temperature, and it was also sometimes called the Kelvin scale of temperature. We have already talked about the fact that the temperature scales we were using before, they were not very reliable. That was because these temperature scales were dependent upon some physical quantity, and that physical quantity was not varying linearly. So the only two temperatures at which these different thermometers were agreeing or giving the same value were the lower fixed point, the ice point, and the upper fixed point, that is the steam point. Which means that if you go to the market and you buy 5 different thermometers and you would want to measure the temperature of a particular body, all those 5 thermometers will give you slightly different values. They wouldn't agree on one single value. Whereas if you would use all of those 5 different thermometers to measure the temperature of melting ice, they will give the same value, 0, or because that's where they're marked from. Or if you measure them to, if you use them to measure the temperature of steam, then they would also give you the same value. So there was a need to have some standard scale of temperature, which is this thermodynamic scale. And this scale is just merely a theoretical scale, which means that you can't go to the market and say that I want a standard scale of thermometer so that I can measure the standard accurate value. This is just a theoretical value of every single, it can be obtained theoretically, but this value or this calibrated value thermometer does not physically exist, as it's a theoretical thermometer and it doesn't depend upon any thermometric property. Like every other thermometer, this scale also has 2 fixed points, the upper fixed point and the lower fixed point. But that's different again. The lower fixed point is taken as the temperature at which the particles have no kinetic energy. So, and that also is a temperature that I mean, you can achieve temperatures very close to that, but you have not been able to achieve the temperature at which the particles have no kinetic energy. So it's just a theoretical value. Practically speaking, you can't have molecules with 0 kinetic energy. So this temperature is obtained by plotting a graph of PV on the y-axis and temperature on the x-axis. So when you plot a graph and you extrapolate the graph to see where it hits the horizontal temperature axis, you would find the lower fixed point of this particular scale, which is called the absolute 0. Reason being, that is the point where the particles is theoretically supposed to have 0 kinetic energy. So you take different gases at different values of pressure and volume, and you plot their graphs, but eventually you'll see that all of these graphs meet at one point, and that is the absolute 0 of the temperature. And that's also going to be the lower fixed point. Since it is a standard scale and we want to have an improved scale, so we wanted to have a better upper fixed point as well. So instead of taking an ice point, we take another temperature, which is slightly different than ice point, and that is called the triple point of water. This triple point of water is obtained in a concealed glass chamber where you have the 3 states of water, which is, of course, the liquid, the solid, which is the ice state, and the water vapors coexisting together. So you take this is made up of glass jacket, and the glass jacket has water in it. You put some sort of freezing mixture over here to make it freeze, and that could be solidified carbon dioxide. And once you put the freezing mixture, the water would start solidifying inside the glass jacket. But as you would see a mixture of water and ice, you also should know that the empty space should have some water vapors existing as well. So, and the best part of this arrangement is that this is less dependent upon the external pressure because it's a concealed chamber. And you should know that the melting point and the boiling point of different substances are being affected by the external conditions of pressure. So we have made it independent by using a triple point cell. So guys, once we use this triple point cell and we get a temperature, that temperature comes out to be slightly above the melting point. On a scale, it is 0.01 degrees Celsius above. But that's the triple point, and that is going to be our upper fixed point. Since we are defining a new scale, so instead of defining it in degrees Celsius, we define it in Kelvin, and we take the lower fixed point, which was the absolute zero, we call it 0. When taking it as minus 273.15. And we choose the upper fixed point, which is the ice point, and we could have given it any value, by the way. But we chose to give it a value which is 273.16. Initially seems to be, you'd say, a little awkward value because, I mean, if I had to choose, I could choose any value. So why 273.16? Again, there's a reason behind that. Because from the lower fixed point to the upper fixed point, if you see a change in degrees Celsius scale, that's 273.16. So it was planned to have a same change in Kelvin as well, which gives you an advantage in terms of an easier conversion from Celsius to Kelvin, and also knowing that every time a change in degrees Celsius of any temperature would be equal to a change in Kelvin. So that also gives you a formula for the interconversion of Kelvin and Celsius, which is the differences of 273.15. Although it's a theoretical scale, but the temperature values can be determined. And those temperature values could be determined by, again, using one of the points, which is temperature of triple point, which is 273.16, and of course the value of PV at that point. So I would say, well, I have one value. Remember now, guys, your coordinate axis origin has shifted quite to the left. So for the new scale, this is your origin. The line is actually passing through the origin because this is where you're taking the temperature in Kelvin to be 0. So if I have one point over here, which is 273.16, and PV at triple point, and let's say there is any random temperature that I want to find out, call it T, and there would be a value of PV at that temperature. So I could say, because it's a straight line linear graph, so I could say that PV at triple point over 273.16 is equal to PV at any temperature over the value of temperature. Now I can sort of rearrange this equation to get myself the value of temperature that I need to find out. And the value of temperature would be PV at any temperature over PV product of pressure and volume at the triple point times 273.16. And then if I'm using a constant volume gas thermometer to get these values, the factor V will cancel out because it's a constant volume gas thermometer. So it has a constant volume. So it becomes PT over PTR times 273.16. So guys, what is the idea? The idea is that if I want, I don't have any physically existing thermodynamic scale thermometer that I'll go to the market and I'll say, okay, let's fetch it and then use it to measure any temperature. But I have a theoretical formula through which I can sort of find out any temperature under the thermodynamic scale. And what do I need to do for that? I'll take a constant volume gas thermometer, I'll measure the pressure at the unknown temperature, I'll measure the pressure at the triple point, and then I'll put it in the formula to get the temperature, which is PT over PTR times 273.16. But you can say at this point, sir, you were saying in the beginning that this thermometer was independent of any physical property, but aren't we using the pressure of a gas? So to try and get rid of that factor as well, what we actually do is that we take an ideal gas. And then you say, well, sir, there is no ideal gas. It's just again, imaginary gas. So what you do is that since there's no gas that's ideal, so you take a gas which would be close to ideal condition. So you would say, sir, the gases which are lighter being observed at lower pressure would have their behavior very similar to the behavior of an ideal gas. So in our constant volume gas thermometer, we take a lighter gas, maybe hydrogen or helium, and at a very low pressure. There we expect it to behave more like an ideal gas. And even in that case, guys, since you're looking to find out the factor of PT over PTR, you don't even say that I'm going to just find out one value of PT over PTR. What you do is that you lower the pressure in the constant volume gas thermometer and get different values of PT over PTR. It's a very, very long, tiring job, but that's why you never want a standard value all the times. You know there is a standard value, you know theoretically it exists, but you can reproduce that by going through this long, tiring process. So you will get PT over PTR by reducing the pressure inside the constant volume gas thermometer. And once you reduce the pressure and you get the values of PT over PTR, and then you extrapolate the graph, then this is the value of PT over PTR where the pressure is almost approaching zero. And when the pressure is almost approaching zero, the behavior of the gas would be almost approaching the behavior of ideal gas. And that's how you know that theoretically, using a formula, I could find out the temperature of any particular body using a thermodynamic scale, which I'm not using all the time, because for me, as far as utility is concerned, the best way is to use any thermometric thermometer, which depends on thermometric property.